Hello friends, welcome to Abaqus Acumen for quick and sound learnings. In this video, I will quickly show you how to apply a hydrostatic pressure load on this water storage tank. So due to this application of linearly varying hydrostatic pressure, you can see the stress distribution on this tank wall, and at the bottom you see the highest stress, and then how you go on the top. So there is the pressure drops, and the corresponding stresses, 1 meter stresses, also tend towards 0. And in Abaqus static or Abaqus standard, so this example we can go through, and in Abaqus it is very easy to apply hydrostatic pressure by knowing the pressure intensity, the highest pressure intensity, and then giving the coordinates, that is 0 pressure reference coordinate for the top, and the highest pressure reference coordinate, that is at the bottom. Quickly, I will give you some recap points. So, and it is very interesting to know, like due to this hydrostatic pressure, you can imagine a small storage pot, and obviously there will be hydrostatic pressure inherently is being exerted on the wall of this pot. And if you make a hole from top to bottom, at the bottommost point you see the pressure, how the liquid is been discharged as the higher speed, and then how you go towards the upward direction, the pressure drops, and the corresponding the speed, that is the discharge speed, also reduces. So this is one of the interesting example, just to give a quick recap to you. And then if you imagine a dam pressure, so again at the top it's 0, and then how you go towards the deeper and deeper, the pressure intensity varies linearly and it increases, and you see the highest at the bottom. And to counter this kind of pressure load, the dams are typically constructed in a taper form, so that it can withstand this higher loads at the bottom. And then this is another a simple example where you have this basement and happen to be with surrounded by the water. So one has to consider this hydrostatic water, which is continuously being exerted over the lifetime of this basement, and to avoid this kind of cracks, one has to consider and design such a way that it should withstand this hydrostatic pressure. And coming back to the simple equations, is same thing over here. So at the top there is no pressure, and then how you go towards the depth of the water, there is the pressure increases linearly with the height, and it is the maximum pressure is being exerted at the bottommost point of the water or the liquid. And the density, so the pressure is equal to rho gh. So this is the equation or the formula for to calculating the pressure, hydrostatic pressure. So here the rho is the density of the liquid. For water it is 1000 kg per meter cube, and g is gravity acceleration, that is 9.81 meter per second square, and h is the height of the liquid column in meters. Abaqus example I'll quickly show you, like this is very straightforward tutorial, just to give you the physics of the problem. We have this storage tank which is made up of HDPE material, that is high density polyethylene material. This is the very regularly used material for building the water storage tanks. The dimensions are like 500 mm is the diameter, and the g coordinates, at the bottom is when we really draw in the Abaqus CAE, then we'll take care, like we'll start with minus 100 millimeter at this point. How you increase the height, it will the g will be 500 millimeter. Okay, and the total distance, that is the height, will be 600 millimeter. So the coordinates will be minus 100 will start, and then we'll stop at 500 in a positive g direction coordinate system. Just to, so with the formula, rho gs formula, so the pressure is 5888 MPa, sorry 5888 Pascal, that is Newton per meter square, and if you convert to MPa, just multiplied by e raised to minus 6, that is Newton per millimeter square. So this is the pressure we're going to apply on a wall of this tank. And for HDPE tank, we'll consider point thickness, we'll be considering 0.6 millimeter, and the density is 1.2 e raised to minus 9 tons per millimeter cube. The unit system we'll be following is Newton ton millimeter and second, and we are going to solve in Abaqus standard. Okay, let's get back to the Abaqus CAE 6.12 preprocessor. Okay, let me start with a blank canvas. So I'll quickly draw. This is very straightforward geometry. So deformable extrusion shell. Continue. So we'll draw a circle with a diameter of 500 millimeter. 250 is the radii. So 600 millimeter. Okay, so we are to extrude by 600 millimeter. Okay, this is done. And then I will go to property. The property is HDPE. Density is 1.2 e raised to minus 9. As this is a static problem, implicit static problem, so even if you don't give density, that should be fine. And the modulus for this HDP is 1500 MPa, and the Poisson's ratio is, we'll assume as the 0.32. So this is about material, and then we'll go to the defining the cell thickness. Okay, 0.6 is thickness. Then we'll apply to this this wall, and this is done. Then we'll go to assembly. In assembly we make instance, and now we'll just to show you, because as I mentioned, we are going to start with a -100 as a G coordinate. So I'm trying to add some complexity so that it will be very clear when you apply hydrostatic pressure in Abaqus CAE. So there would be some cases where it may not be always be at a 0 G coordinate. There would be some real scenarios you may get the coordinate at the bottommost may be in a negative G coordinate as well. So I'm just translating by -100 in G direction. Okay, this is done. This is okay, and now we'll create a step. This is static general, so usually by default it is static general. Just say continue and just say okay. This is done, and then you go to load, and here we need to apply. So this is the most critical step in this tutorial, that is application of pressure, that is hydrostatic pressure. Say continue, and here you have to select the wall. Okay, and say the purple, that is the inner side is a purple. Choose this one, and here you choose hydrostatic. Okay, and the magnitude we know it is 0.588 MPa, and the height. Okay, so here, so the best way is we already know it is bottommost G coordinate is -100. So just to check in this okay, so this is the point, bottommost point where with the highest pressure. This is the bottommost point, and then we will select the topmost. So you can see here the point 1, the G coordinate is -100, and then we have the the bottommost is a -100 where the highest pressure is being applied, and then at the top it is 500 millimeter, that is a G coordinate. Okay, and here you have to choose the hydrostatic, and then as I mentioned, the highest bottommost pressure is 0.00588. that is we calculated through this formula of rho GH, and the zero pressure height is, okay, when we say this is a water column, so the coordinate is 500 and the reference is -100 where the pressure is the maximum. Okay, just say simply okay, done. So this is the most critical step in this tutorial. So this is done, and now we're going to apply bonding condition. At the bottom we are going to hold this. So as this, imagine this tank is rested on some floor. So just for simplification, so select this edges, done, and I'm going to encaster this. Okay, and I'll go to the mesh tool. Okay, this is a need to make this instance independent. For that go to assembly and make this part independent. Okay, so 25 millimeter size is suitable for this geometry. say yes, done. Okay, so that's it. So we're going to submit a job. Okay, job 77, some name I have to give, so just leave it to defaults, say submit. Okay, job is completed successfully. Then just say results. So alright, so this is the result with us. So I'll just put it in right coordinates, so you can see at the bottom we have maximum stresses where the pressure is high, and then the pressure is linearly varying. At the top you have give you one teaser. Okay, so there are I mean instances where you have a tank and with some baffles. Okay, so this tank is being subjected to the hydrostatic pressure, and in baffle, okay, even though it is centrally, it is located somewhere in this location, and obviously we tend to think that, okay, why don't we apply a hydrostatic pressure on that, but just for I'm sure we are smart enough to know that as the pressure is being applied on the both side, because the water is fully covering this baffle. So obviously the pressure exerted from this side and the other side is being balanced out. So when we do this kind of simulation, just ignore the baffles from the application of the pressure load. Okay, so this is just a gentle reminder for you. Guys, I hope you found this tutorial useful. This is a very simple tutorial, and just you can always refer this step, and once you know this, you can do on your own. So thanks a lot, and please like this video, and also please subscribe our channel Abaqus Acumen, so that we'll keep bringing you the new videos. Thank you, bye bye.